Creating an ensemble of learners is one way to make the learners you've got better. So we're not talking about creating a new algorithm, but instead assembling together several different algorithms or several different models to create an ensemble learner. One thing I want to emphasize here is that you can take what you learn here about ensemble learners and plug it right into what you're already doing with your KNN and linear regression models. Now, what we've been doing so far is we've had one kind of learning method, say KNN. We plug our data into there and we learn a model. We can query our model with an X and it'll give us a Y. So this is not an ensemble learner, this is just a single learner. And the idea with ensemble learners is that we have several additional learners. So we might have a linear regression-based model, we might have a decision tree-based model, we might have a support vector machine-based model. You could continue this on with any different number of algorithms. They're all trained using the same data, and so now we have, in this case, 4 different models. To query this ensemble of learners, we query each model by itself and combine the answers. So if we want to query this model with X, we plug X into each model, the same X, and then our Y's come out. So we have a Y output from each of these models. How do we combine them? If we're doing classification, where, for instance, we're trying to identify what the thing is, we might have each of these Y's vote on what it is. But we're doing regression, and so the typical thing to do here is to take the mean. And that is the result for this ensemble learner. We can then test this overall ensemble learner using this test data that we set aside. Why ensembles? Why do we use them? Why might they be better? Well, there's a few reasons. First of all, ensembles often have lower error than any individual method by themselves. Ensemble learners offer less overfitting. The ensemble of learners typically does not overfit as much as any individual learner by itself. Now, why is that? Here's at least an intuitive answer. Is each kind of learner that you might use has a sort of bias. It's easiest to talk about that in terms of linear regression, in terms of what do I mean by bias. So clearly, with linear regression, our bias is that the data is linear. KNN has its own kind of bias, decision trees have their own kind of bias. But when you put them together, you tend to reduce the biases because they're fighting against each other in some sort of way. Anyways, that's what an ensemble learner is like if we use multiple types of learners. There's another way we can build an ensemble of learners. We can build them using the same learning algorithm, but train each learner on a different set of the data. This is what's called bootstrap aggregating or bagging. It was invented by Bremen in the late 80s, early 90s. Here's how bagging works. So what we do is we create a number of subsets of the data. I've drawn little bags here to represent bags of data. And each one of these is a subset of the original data. Now, how do we collect these? Well, we do it randomly. So for this subset that contains n prime values, and our original data set contains n different instances, we grab n prime of them at random with replacement from this original data. So what with replacement means is, let's say we had, these values. We might grab this one and put it in our bag. We might randomly grab this one and put it in our bag. But each time we grab randomly, we randomly choose across the whole collection of data. So we might choose this one again and put it in the bag. So this one and this one are really the same one, and they're repeated twice. And that's okay. That's what with replacement means. So we create all together M of these groups or bags, and each one of them contains n prime different data instances chosen at random with replacement. Let's note these things. So n is the number of training instances in our original data. N prime is the number of instances that we put in each bag, and m is the number of bags. We almost always want n prime to be less than n, usually about 60%. So each of these bags has about 60% as many training instances as our original data. That's just a rule of thumb. Now we use each of these collections of data to train a different model. We have now m different models, each one trained on a little bit of different data. And just like when we have an ensemble of different learning algorithms, here we have an ensemble of different models. We query in the same way. We query each model with the same x, and we collect all of their outputs. We take the y output of each model, take their mean, and boom, that's our y for the ensemble. Now, keep in mind, we can wrap this in a single API, just like that API you wrapped your linreg learner in and your KNN learner in. So suppose this is some example data, and we're going to create a bunch of one nearest neighbor models. We first have to select randomly some of our data to go into the first bag. So I'm going to circle some of these points randomly that represent the data for our first model. So we randomly selected some of these points. Now let's show what that model looks like. So this zigzagging orange line here represents what that one nearest neighbor model would look like. And yes, to me it looks like it's overfitting, but that's just our first model. Then we draw some more data and we have another model. So our other model, model 2, is somewhat overfitting as well. But let's consider now a ensemble model where we combine the results of these two. And at each point where we query, remember what we do is we take the mean of the two models. So you can see already, as this blue curve is a bit more smooth than the individual models, we're beginning to get something better. But let's add some more models. So I've drawn over here a couple more one nearest neighbor models, and you can see each one of them individually is sort of overfit. But if we now sample at each individual spot across here and take the average across all of them, we get something that's much more smooth. So here's what our ensemble looks like, and as you can see, it's much more smooth. Of course, I hand drew it so you could accuse me of smoothing it by hand. Anyways, the point here is that you can build an ensemble that is much more smooth than any of the individual learners by themselves. Boosting is a fairly simple variation on bagging that strives to improve the learners by focusing on areas where the system is not performing well. One of the most well-known algorithms in this area is called AdaBoost, and I believe it's ADA, not ADA, because ADA stands for adaptive. Here's how AdaBoost works. We build our first bag of data in the usual way. We select randomly from our training data. We then train a model in the usual way. The next thing we do, and this is something different, we take all of our training data and use it to test the model. And we're going to discover that some of the points in here, our x's and our y's, are not well predicted. So there's going to be some points in here for which there is significant error. Now, when we go to build our next bag of data, again we choose randomly from our original data, but each instance is weighted according to this error. So these points that had significant error are more likely to get picked and to go into this bag than any other individual instance. So as you see, we ended up with a few of those points in here and a smattering of all the other ones as well. We build a model from this data and then we test it. Now we test our system all together. In other words, we've got a sort of miniature ensemble here of just 2 learners, but we test both of them. We test them by inputting, again, this in-sample data. We test on each instance and we combine their outputs. And again, we measure error across all this data. Maybe this time these points got modeled better, but there were some other ones up here that weren't as good. And thus we build our next bag and our next model. And we just continue this over and over and over again up until M, or the total number of bags we're going to be using. So to recap, bagging, when we build one of these instances, is simply choosing some subset of the data at random with replacement, and you create each bag in the same way. Boosting is an add-on to this idea where in subsequent bags we choose those data instances that had been modeled poorly in the overall system before.
This stat quest assumes you already understand decision trees, so if you're not already down with those, check out the quest. This stat quest also assumes that you are familiar with AdaBoost and the trade-off between bias and variance. If not, check out the quests. The links are in the description below. This stat quest is the first part in a series that explains how the gradient boost machine learning algorithm works. Specifically, we'll use this data, where we have the height measurements from 6 people, their favorite colors, their genders, and their weights. And we'll walk through, step by step, the most common way that gradient boost fits a model to this training data. Note, when gradient boost is used to predict a continuous value, like weight, we say that we are using gradient boost for regression. Using gradient boost for regression is different from doing linear regression, so while the two methods are related, don't get them confused with each other. Part 2 in this series will dive deep into the math behind the gradient boost algorithm for regression, walking through it step by step and proving that what we covered today is correct. Part 3 in this series shows how gradient boost can be used for classification. Specifically, we'll walk through, step by step, the most common way gradient boost can classify someone as either loving the movie Troll 2 or not loving Troll 2. Part 4 will return to the math behind gradient boost, this time focusing on classification, walking through it step by step. Note, the gradient boost algorithm looks complicated because it was designed to be configured in a wide variety of ways. But the reality is that 99% of the time, only one configuration is used to predict continuous values like weight, and one configuration is used to classify samples into different categories. This stat quest focuses on showing you the most common way gradient boost is used to predict a continuous value like weight. If you are familiar with AdaBoost, then a lot of gradient boost will seem very similar. So let's briefly compare and contrast AdaBoost and gradient boost. If we want to use these measurements to predict weight, then AdaBoost starts by building a very short tree called a stump from the training data. And then the amount of say that the new stump has on the final output is based on how well it compensated for those previous errors. Then AdaBoost builds the next stump based on errors that the previous stump made. In this example, the new stump did a poor job compensating for the previous stump's errors, and its size reflects its reduced amount of say. Then AdaBoost builds another stump based on the errors made by the previous stump. And this stump did a little better than the last stump, so it's a little larger. Then AdaBoost continues to make stumps in this fashion until it has made the number of stumps you asked for, or it has a perfect fit. In contrast, gradient boost starts by making a single leaf instead of a tree or stump. This leaf represents an initial guess for the weights for all of the samples. When trying to predict a continuous value like weight, the first guess is the average value. Then gradient boost builds a tree. Like AdaBoost, this tree is based on the errors made by the previous tree. But unlike AdaBoost, this tree is usually larger than a stump. That said, gradient boost still restricts the size of the tree. In the simple example that we will go through in this stat quest, we will build trees with up to 4 leaves, but no larger. However, in practice, people often set the maximum number of leaves to be between 8 and 32. Thus, like AdaBoost, Gradient Boost builds fixed-size trees based on the previous tree's errors, but unlike AdaBoost, each tree can be larger than a stump. Also, like AdaBoost, Gradient Boost scales the trees. However, Gradient Boost scales all trees by the same amount. Then Gradient Boost builds another tree based on the errors made by the previous tree. And then it scales the tree. And Gradient Boost continues to build trees in this fashion until it has made the number of trees you asked for or additional trees fail to improve the fit. Now that we know the main similarities and differences between Gradient Boost and AdaBoost, let's see how the most common Gradient Boost configuration would use this training data to predict weight. The first thing we do is calculate the average weight. This is the first attempt at predicting everyone's weight. In other words, if we stopped right now, we would predict that everyone weighed 71.2 kilograms. However, Gradient Boost doesn't stop here. The next thing we do is build a tree based on the errors from the first tree. The errors that the previous tree made are the differences between the observed weights and the predicted weight, 71.2. So let's start by plugging in 71.2 for the predicted weight, and then plug in the first observed weight, and do the math, and save the difference, which is called a pseudo-residual, in a new column. Note, the term pseudo-residual is based on linear regression, where the difference between the observed values and the predicted values results in residuals. The pseudo part of pseudo-residual is a reminder that we are doing Gradient Boost, not linear regression, and is something I'll talk more about in part 2 of this series when we go through the math. Now we do the same thing for the remaining weights. Now we will build a tree using height, favorite color, and gender to predict the residuals. If it seems strange to predict the residuals instead of the original weights, just bear with me and soon all will become clear. So, setting aside the reason why we are building a tree to predict the residuals for the time being, here's the tree. Remember, in this example, we are only allowing up to 4 leaves. But when using a larger data set, it is common to allow anywhere from 8 to 32. By restricting the total number of leaves, we get fewer leaves than residuals. As a result, these 2 rows of data go to the same leaf. So we replace these residuals with their average. And these 2 rows of data go to the same leaf. So we replace these residuals with their average. Now we can combine the original leaf with the new tree to make a new prediction of an individual's weight from the training data. We start with the initial prediction, 71.2. Then we run the data down the tree, and we get 16.8. So the predicted weight equals 71.2 plus 16.8, which equals 88, which is the same as the observed weight. Is this awesome? No, the model fits the training data too well. In other words, we have low bias, but probably very high variance. Gradient Boost deals with this problem by using a learning rate to scale the contribution from the new tree. The learning rate is a value between 0 and 1. In this case, we'll set the learning rate to 0.1. Now the predicted weight equals 71.2 plus 0.1 times 16.8, which equals 72.9. With the learning rate set to 0.1, the new prediction isn't as good as it was before. But it's a little better than the prediction made with just the original leaf, which predicted that all samples would weigh 71.2. In other words, scaling the tree by the learning rate results in a small step in the right direction. According to the dude that invented gradient boost, Jerome Friedman, empirical evidence shows that taking lots of small steps in the right direction results in better predictions with a testing data set, i.e., lower variance. Bam! So let's build another tree so we can take another small step in the right direction. Just like before, we calculate the pseudo-residuals, the difference between the observed weights and our latest predictions. So we plug in the observed weight and the new predicted weight, and we get 15.1. And we save that in the column for pseudo-residuals. Then we repeat for all of the other individuals in the training data set. Small bam. Note, these are the original residuals from when our prediction was simply the average overall weight. And these are the residuals after adding the new tree scaled by the learning rate. The new residuals are all smaller than before, so we've taken a small step in the right direction. Double bam! Now let's build a new tree to predict the new residuals. And here's the new tree. Note, in this simple example, the branches are the same as before. However, in practice, the trees can be different each time. Just like before, since multiple samples ended up in these leaves, we just replace the residuals with their averages. Now we combine the new tree with the previous tree and the initial leaf. Note, we scale all of the trees by the learning rate, which we set to 0.1, and add everything together. Now we're ready to make a new prediction from the training data. Just like before, we start with the initial prediction. Then add the scaled amount from the first tree and the scaled amount from the second tree. That gives us 71.2 plus 0.1 times 16.8 plus 0.1 times 15.1, which equals 74.4, which is another small step closer to the observed weight. Now we use the initial leaf plus the scaled values from the first tree plus the scaled values from the second tree to calculate new residuals. Remember, these were the residuals from when we just used a single leaf to predict weight. And these were the residuals after we added the first tree to the prediction. And these are the residuals after we added the second tree to the prediction. Each time we add a tree to the prediction, the residuals get smaller. So we've taken another small step towards making good predictions. Now we build another tree to predict the new residuals, and add it to the chain of trees that we have already created. And we keep making trees until we reach the maximum specified, or adding additional trees does not significantly reduce the size of the residuals. Bam. Then, when we get some new measurements, we can predict weight by starting with the initial prediction, then adding the scaled value from the first tree, and the second tree, and the third tree, etc., etc., etc. And once the math is all done, we are left with the predicted weight. In this case, we predicted that this person weighed 70 kilograms. Triple bam! In summary, when gradient boost is used for regression, we start with a leaf that is the average value of the variable we want to predict. In this case, we wanted to predict weight. Then we add a tree based on the residuals, the difference between the observed values and the predicted values. And we scale the tree's contribution to the final prediction with a learning rate. Then we add another tree based on the new residuals. And we keep adding trees based on the errors made by the previous tree. That's all there is to it.
이번 참조 동영상에서는 앙상블, 배깅, 아더 부스트, 그라디언 부스트에 대해서 알아보았습니다. 이번 강의에서는 앙상블 테크닉에 대해서 간단히 알아보도록 하겠습니다. 앙상블 방법은 트레이닝 데이터로부터 a set of classifiers, 분류기의 집합을 구성하는 것입니다. Predict class label of test records, 테스트 레코드의 클래스 레이블을 예측하는데 by combining the predictions made by multiple classifiers, 다중 분류기로부터 예측된 값들을 결합합니다. 앙상블 분류기를 만드는 방법은 오리지널 트레이닝 데이터에서 스텝 1에서는 multiple dataset을 만들고 스텝 2에서는 multiple classifier를 빌드하며 스텝 3에서는 이러한 클래시파이어 결과들을 컴바인하는 것입니다. 앙상블을 구현하는 방법으로는 데이터 디스트리뷰션을 머니플레이트하는 방법이 있습니다. 배깅과 부스팅이 이에 해당됩니다. 인풋 피처를 머니플레이트하는 것은 랜덤 포레스트라고 합니다. 클래스 레이블을 머니플레이트하는 것은 에러 커렉팅, 아웃풋 코딩이라고 합니다. 멀티클래스 프로블럼을 풀기 위해서 바이너리 클래시파이어들을 컴바인할 때 사용됩니다.